Bismillah ar-Rahman ar-Rahim. Now we will talk about RC circuits. It is the type of circuit which contains resistors and capacitors. So this is called RC circuit. So this is my capacitor connected to a resistor. And also we have an EMF device. Here we have a switch. The switch, when it is connected at A, we call this process to be charging of the capacitor. Okay, and after we charge the capacitor, we can put the switch on position B. The capacitor will discharge. Let me start with charging of the capacitor. Charging of the capacitor. Let me draw it clearly here. This will be the situation. Okay, so the circuit, we start with a charge equal 0 initially at t equals 0 at the beginning of the experiment, just by putting the switch on A at the very beginning. Q is equal to 0, so there was no charge originally at this capacitor. Finally, after some time, as you can see, this will be positively charged, this side, and this side will be negatively charged, meaning that the electrons will escape from this plate and will go on the other side and will accumulate on the negative side of the capacitor until the capacitor is fully charged. Okay, in order to find the rate at which the capacitor is charging and check the loop rule here, we can apply the loop rule on this loop. So would like to move and see how does the electric potential change as we move along this circuit. Okay, so we can do it such that I am moving from the negative side of the EMF to the positive side, so we will experience plus. So apply loop rule. As a result, we'll get plus E, because I am moving from the negative to the positive side of the EMF. Then the current is moving in this direction, I. So we'll experience a negative or a drop in the electric potential, and that is equal minus I R. And as we move from the positive side of the capacitor to the negative side, we'll experience a drop in the electric potential. Okay, so as we move this way, there will be a drop, and this is minus V. What is V of a capacitor? Remember, my son, that C equals Q over V. So V, which is the potential difference, can be written as Q over C. So if you move this way, this will be minus Q over C. If you move the other way, that will be plus Q over C. Okay? We treat it as we treat the EMF. Moving from negative to positive will give you potential increase. Moving from positive to negative, this will give you potential drop. So right now, this is my loop. I have potential increase, potential drop, and here potential drop. So this is minus Q over C. Then we reach the original point, so this is equal to 0. But what is I? We know from our discussion in previous videos that I is dQ by dt. So we can replace this I as dQ by dt. So we can write that E equals R dQ by dt, which is IR on the other side, plus Q over C. So this type of equation, we call it differential equations. Okay, so this is differential equation, and it has a solution. You will study it later on in your math course, and it has a solution of the following form. The solution of this differential equation, looks like the following. Q equals C E multiplied by 1 minus e to the minus t over RC. Okay? Q, the charge on this capacitor at any time, equals C, which is capacitance of this capacitor, multiplied by E, the E of the EMF device, multiplied by 1 minus e to the minus t over RC. Let us check what does this equation say. If the time equals 0, t equals 0, and the plug here 0, anything to the power 0 will give you 1. So 1 minus 1 will give you Q equal 0. So this will be C E 1 minus e to the 0, anything to the 0, this will be 1, and this will give us the charge equals 0 when the time is 0. So this is okay with us. Finally, if the time is very large, let us say time is infinity. Okay, when the time is infinity, so this is e to the or 1 over e to the power infinity, very large number, because here e to the minus time, or it is 1 over e to the power infinity. So this term will be equal to 0. Okay, so this will give us Q equals C E multiplied by 1 minus 1 over e to the power infinity. So this is very large number. So this term will go to 0, and we are left with the following. This is the maximum charge the capacitor will gain when the time is very large. At that moment, C, it will be equal to C multiplied by E of the EMF. Okay, so this is a very important result. Okay, we start at the very beginning with 0 charge on our capacitor. It increases until it reaches the maximum value, and it is equal to CE. What will happen when our capacitor reaches the maximum charge? No more charges will accumulate, and at that moment we'll say that there is no current passing through. So the charging process will stop. Charging process will stop, meaning that there is no movement of charges, and the current will be equal to 0 when the time is equal to infinity. After some long time, the charge will be maximum, and there is no more charging in our capacitor, and it will be the current will be equal to 0. What can we say about the current? The current, we can give expression for the current. We know that current equals dq by dt. Here we have q as a function of time. Okay, this is q as a function of time. If we take the derivative with time, this will tell us how the current changes upon charging our capacitor in this in such a circuit. Okay, taking the derivative will give us the following. Derivative will give us I equals E over R multiplied by e to the minus t over RC. What do you notice about this? It will start when the time equal 0, we will have the maximum. So if time equal 0, this will be 1, and I will be maximum, and this is equal to E over R. But if the time is very large, goes to infinity, we wait for a long time, this term will be 0, and the time will be, the current will be 0. Okay, so no current will pass through the circuit after a long time. If you would like to find an equation to get an idea about the electric potential across our capacitor, what happens to V? We know that at the very beginning V equals Q over C, but Q was 0, so V will be 0. Okay, after some time it will increases until we reach the maximum Q, and we end up with V equals Q over C. Let us get how much is V across the capacitor, the potential difference across our capacitor. This is equal to Q divided by C. But this is the formula for Q. So if you divide this with C, C will cancel and we'll end up with the following. It will be equal to E multiplied by 1 minus E to the minus T over RC. Very nice. If the time equals 0, this term will be 0. This term will be 1, and we will get the following. This will give us V across the capacitor equals just E, and when the time equals 0, this is equal to 1, and V is equal to 0. So 1 minus 1 will give us 0. But when the time equals infinity, this will give us, if this is infinity, so 1 over E to the power infinity, this will be 0, and we'll end up finally with V across the capacitor equals just E. Okay, so these are very important relations. One of them telling us how the charge across the capacitor changes with time. As you can see, it is increasing. We start with Q equal 0, and we end up with Q maximum, which is CE. The current, we start with maximum current at the very beginning, okay? And at the end, after a long time, the current will be 0, and the electric potential across the capacitor, we start with 0 value at the beginning, and we end up with a maximum value which is equal to E of the EMF. If you would like to draw these quantities with time, how do they change with time? So for charging the capacitor, we can draw the following. If this is Q versus T, notice that we start with 0, so this is our 0, and we can also draw the current versus time, and we can draw the electric potential across the capacitor with time. Let me use a different color here. For Q, we start with 0 value, and it will go to a maximum value after a long time. What is this maximum value it will approach? That maximum value is CE. Okay, so this maximum value is CE. For the current, we'll start with a maximum value, which is E over R. Then finally, after a long time, it will be 0. So we start with maximum value here, and it decays until it reaches 0. And this maximum value is just E over R. Okay? And for the electric potential, we start with 0 at time equals 0. And finally, we reach to maximum value, which is E of the EMF. So this is nothing but E of the EMF. After a long time, we will reach this maximum value. By the way, there is a special name for this quantity, which is RC. Okay, so let me write for you here. What do we mean by RC? RC is called time constant. Time constant. And it has a special symbol, which is tau. Tau equals RC. What is the unit of this time constant? It should have the same unit as the time. Okay, so it has units of seconds. So ohm multiplied by farad, this is nothing but a second. Okay, and it tells us how long does it take to charge a capacitor. If this product is small, so tau is small, what does it imply? If tau is small, this implies quick or fast charging of the capacitor. Okay? If tau is large, this tells us that it will be slow charging of the capacitor. Okay, we can see the following: Q equals if t equals tau, if the time equals RC. So this will be e to the minus 1. Okay, and this will be 1 over e. So Q, this implies that Q will be C E multiplied by 1 minus e to the minus tau over tau, which is minus 1. And this will give us 0.63 Q max. Okay, so we can define the time constant as the time needed to charge our capacitor to 63% of its maximum value. So if this time is small, you will reach the 63% in very short time. If it is long, if it has big number, the time needed to reach 60% of the maximum charge will be larger. So I hope now you have a useful understanding of what we mean by charging a capacitor. How does the charge change with time? How the current changes with time? How across the capacitor changes with time? And what we mean by the time constant of a capacitor. In a few minutes, we'll have another video to talk about discharging of a capacitor. Now we start talking about a capacitor discharging. Previously, the EMF was connected to the resistor, capacitor, and now the capacitor is fully charged and it carries the maximum charge, or what we call Q0. Okay, now I'll put the switch on point B here. Okay, so it is not connected to the EMF anymore, and right now our capacitor will discharge across this resistance. Okay, and the current is passing this way because the negative charges will go that way, and the conventional current will be opposite to the motion of the negative charge. So the current is going this way, and we can apply the loop rule in this direction, and we can write that how much is the potential change as we move from the negative to the positive. So this is plus Q0 over, so this is plus Q over C minus I R. This is equal to 0. So this is the loop rule. And we can replace the current with dq by dt. So we can write this dq by dt multiplied by R equals Q over C. And this is another differential equation, and we can solve this differential equations as follows. Q will be found to be Q0 e to the minus t over RC. Let us check when the time is 0. For time equals 0 at the very beginning, if this is 0, the term will be 1. This implies that Q equals Q0. So we started with the charge which is Q0 of our capacitor. It makes sense. If the time is, we wait for a long time, Q will be equal to 0. Okay, because this will be 1 over e to the power infinity, very large number. 1 over very large number will give us 0, and Q will be equal to 0. So the charge will be decaying as time increases, and it makes sense. So this is the solution we get from this formula. What about the current? Current will be dq by dt, and this can be written as Q0 over RC. There is a minus sign. It tells you about the direction of the current. Q0 over RC e to the minus t over RC. So both of them will be decaying. The charge will be decaying and the current will be decaying. We'll start with large current at time t equals 0. So time t equals 0, the current will be maximum. So this term will be 0, and I equals Q0 over RC. And if the time we wait for a long time, the current will be equal to 0. Okay? If you want to see how does the electric potential across the capacitor with time, we know that Vc will be the original or the initial electric potential, which we call the V0, and with time it will decrease as minus T over RC. So if the time equal 0 at the very beginning, just right after putting the switch from A to B, at that moment time just started equal 0, and Vc will be equal to V0, the initial potential. And as the time increases, after a long time, when our capacitor is fully discharged, Vc will be equal to 0. So these are the different equations we have for the charge on our capacitor and how it changes with time, the current in the loop, and how does it change with time, and Vc. All of them are decaying. If you want to plot them, you can plot Q. So this is Q versus T. We can plot I versus T. We can also plot V versus Vc. This is the potential across the capacitor versus T. We plot them in a different color. All of them will be decaying. So this will go with time. It will reach 0. We start with high value of the current. We start with high value of the electric potential. Here the initial value was Q0. Here the initial value was V0. And here the initial value was Q0 over RC. Over RC. So with this we close the chapter, and I would like to emphasize on something. You will see, my son, in the problems for the RC circuit. If you have RC circuit, something like this, you have a battery, okay, and you see resistance, okay, and here you have another resistance, okay, and here in this branch you will have a capacitor, okay, and a resistor, okay. So this is capacitor, this is EMF device, and these are resistors R1, R2, R3, okay. If you are given this circuit, and he says after long time, meaning that T equals infinity, what will happen to this capacitor? If we have here a switch, okay, and this switch is closed, and after long time from closing the switch, what will happen to this capacitor? This capacitor will be fully charged. So this capacitor, after a long time, this capacitor will be fully charged. So no more current will pass through this branch. So this branch, at the very beginning, time equals 0, there will be some current, decrease. After a long time, the current here will be 0. So this branch will act as being an open circuit. No current will pass through this side, okay? So no current will pass through the resistance R3, okay? So as if it is not there. So my circuit will end up as if we don't have this branch after a long time. So you will end up with R1 and R2, and this implies that R1 and R2 are connected in series. Inshallah, when we go to problems and solve all the exam problems as practice for you, we will have similar problems, inshallah, and you will fully understand the concept with my best wishes. Thank you.